All right, let's get right into it. Welcome to this comprehensive explainer on EPA Performance Specification 2. If you've ever found yourself wondering exactly how massive industrial facilities prove they're staying within the legal limits for pollutants, things like sulfur dioxide and nitrogen oxides, well, this is the absolute blueprint. We're not just talking about flipping a switch on a machine here, it's a meticulously structured, highly rigorous journey of compliance. And today, we are going to unpack exactly how the whole thing works. Here is our roadmap for this explainer. We'll start with scope and definitions, figure out CEMS installation and location, run through the testing procedures, crunch the calculations and data analysis, and wrap it all up with the performance specifications. Let's hit it. Part 1, Scope and Definitions, the foundation. Gotta know the rules of the game before we actually start playing, right? So the absolute star of the show here is the CEMS, the Continuous Emission Monitoring System. Now keep in mind, this isn't just one single lonely box sitting on top of a smokestack. As the EPA defines it, it's the total equipment required for determining a gas concentration or emission rate. This includes major subsystems like your sample interface, the actual pollutant analyzer picking up that SO2 and NOx, a diluent analyzer, and, crucially, the data recorder, making sure there's a permanent record of the whole shebang. Now, depending on your facility's setup, you're going to run into two main flavors of these systems. Point CEMS measure gas concentration either at a single, specific point or along a really short path, specifically equal to or less than 10% of the stack's equivalent diameter. On the flip side, path CEMS are measuring along a path greater than 10% of that diameter. Why does this matter? Well, it literally dictates precisely how and where you're allowed to measure within that exhaust stack. Okay, check this out. Relative accuracy, or RA, is basically the ultimate report card for your system's performance. It isn't just a simple comparison. It factors in the absolute mean difference between what your CMS reads and what a trusted reference method reads. But it doesn't stop there. You have to add in a 2.5% error confidence coefficient, because, statistics, and divide all of that by the mean of those reference method tests. It is a highly robust mathematical reality check. Moving right along to Section 2, CMS installation and location. Let's look at the actual physical hardware. You can't just drill a hole in a smokestack wherever it's convenient and hope for the best. The EPA is super specific here. To get a truly representative sample, you must select a measurement point at least 2.0 equivalent diameters downstream from the nearest control device, and at least 0.5 equivalent diameters upstream from the effluent exhaust. It's all about making sure the gas flow has chilled out into a predictable, measurable pattern before it ever touches your sensors. And when you're actually testing that flow across the stack, you've got strict traverse point requirements. Let's say your measurement line is a long one, over 2.4 meters, and you aren't expecting the pollutants to be stratified or layered unevenly. The rules give you these alternative traverse points. You measure exactly at 0.4, 1.2, and 2.0 meters away from the stack wall. This means no operator is ever just guessing at the cross-section of the gas flow. All right, Section 3, testing procedures and runs. The equipment is bolted in, so let's start testing. Quick timeout before we get into the actual testing steps. I saw many people are not liking and subscribing to my explainer to motivate me, and honestly, you literally will not find a more detailed EPM method breakdown anywhere on the internet. I am providing you this full explainer overview doing the deepest dive possible, so I really need your support to like and subscribe to my explainer. Okay, let's get back to how the active testing actually goes down. So, the reference method procedure is highly sequential. First up, for integrated samples, you perform a sample traverse of at least 21 minutes. Then, you determine the integrated average concentration from your CEMS output over that exact same time frame. Step 3 is vital. You correlate the CEMS and reference method data by exact time and duration. Finally, calculate the mean difference. It's like perfectly syncing your watch before a heist. Everything has to match up perfectly in time and conditions. And you definitely can't just do this once and call it a day. No way. The EPA mandates a rock-solid minimum of 9 sets of reference method test runs to ensure statistical viability. I mean, 1 or 2 tests could just be a total fluke. 9 starts to build a mathematically undeniable trend. But hey, the real world is messy, right? Equipment hiccups. So the crucial point here is that operators actually have a tiny bit of breathing room. If you run more than 9 tests, the spec allows you to throw out up to 3 flawed sets of results. The catch? You still must end up with a minimum of 9 valid tests. Oh, and transparency is everything here. Every single piece of data, even the rejected garbage runs, still has to be fully reported. Section 4, Calculations and Data Analysis.
time to do some math. First things first, we gotta compare apples to apples. Because all your data needs to be on a consistent dry basis, you first hit your wet runs with equation 2-1, the moisture correction formula. It's simple but absolutely crucial for stripping that variable of water vapor right out of your data. Once your units are dry and may be corrected to the specific units of the standard, we calculate the arithmetic mean. That's equation 2-3. We're literally just taking the sum of all the individual differences between your CEMS data and the reference method data across your valid runs and dividing by the number of data points. Boom, your baseline average difference. Then you take those individual differences and feed them into this somewhat intimidating formula, equation 2-4. Yeah, it looks complex, but it's just finding your standard deviation. It calculates how tightly clustered your CEMS differences are around the mean. The lower the standard deviation, the more consistent and predictable your monitor is. Simple as that. Which brings us to the final act, Section 5, Performance Specifications. This is where all that citing, testing, and math finally pays off for compliance. Depending on how your actual facility emissions stack up against the legal standard, your relative accuracy has to cleanly fall beneath these specific percentage thresholds. If your emissions are over 50% of the standard, your RA has to be less than 20%. But check this out. If your emissions are lower than 50% of the standard, your monitor actually needs to be more accurate, hitting an RA of under 10%. It's a sliding scale of strictness. And we absolutely can't forget about the daily grind, calibration drift. Over a given period of operation, your CMS calibration cannot drift from the certified reference gas value by more than 2.5% of the span value. You definitely don't want your monitor slowly going blind to the actual pollution levels over time. So we've walked through the complex definitions, the exact spatial rules, the mandatory 9+ tests, and some pretty unforgiving math, which leaves us with a massive question to ponder. How do these incredibly strict mathematical tolerances and unyielding spatial rules ensure the ongoing integrity of our global environmental protection efforts? It really proves that protecting the environment isn't just some abstract theory. It is a rigorous, daily mathematical reality that these facilities and operators have to answer to every single hour. What do you think? Thanks for joining me on this explainer. Keep questioning the data, and I'll see you next time.